Yeah.
Good afternoon, everybody.
Afternoon, sir.
Good afternoon, sir.
Afternoon,
Good
sir.
afternoon, sir.
Yes.
Afternoon.
So I was saying, um, today we're going to talk about discrete systems. All right. So it was an introduction. When we take our continuous signal and we sample it, well, every t second, whether t be 1/10 of a second or 100th of a second or a millionth of a second, we sample it and then we send that along. We take that sample and then we take it and make it into a digital signal. In other words, now, when we sample it and we send it along a channel as a digital signal, so we send it as a set of ones and zeros. All right. So that is the way the world has gone. We take a continuous signal, that the sound of my voice, we sample it every couple seconds, so we don't take the entire signal, we sample it, and then we convert each. So let us say that this is 4 volts. Then we convert that 4 volts to a 110 or whatever it is, and we send it along a channel. Now, so that is what we are doing now. Why? Well, for one, if you have anything at all, and you put it up into pieces, then you have less. It will occupy less space. So if I take up the signal and I sample it every 3 seconds, um, and then digitize each of the samples and send them along channel, I can send many more signals along the same channel, because what will happen is that I can have 2 different or 10 different frequencies to send along the same channel. Whereas if so I have 2 different frequency signals, and at the end I just filter them out and take out the ones that I want. So if you cut up, so when a
Sir,
signal, yeah,
question, sir.
mhm,
Looking at it physically,
mhm.
how we send more than one signal through a wire at the same time?
All right, so this is one signal at one frequency, and then now I'm trying to say that this is the same, same signal at a different frequency. So you have 2 different frequencies.
Sir,
And
but
suppose,
if it going through the same wire, it wouldn't be like cause some type of interference.
so they're going to interfere. So at the other end of the wire, you put a filter. So it cut out certain frequencies. So it cut out this frequency, I cut out this frequency, and only this alone is left. So when, for example, when you tune your radio to 99 point whatever hertz, then what you're saying is that there's only signals of that frequency. You're going to filter out throw away everything else.
Oh, so that's why them teach you about the thing, the resonance circuit.
Initially, I want to say yes. I will leave it as yes. All right. So, if for example, with your radio, the telecommunications, you see that at the radio frequency, they can set several different frequencies along the same channel because all you have to do is filter it out at the other end. So filter out everything else, and then well, like they say, you have a notch filter, so it's only one frequency is targeted. So it's that frequency that you want, that you get. So you can send several frequencies along a channel. All right, they're going to interfere, but let's think about it now. If this interfere, so what is going to happen is that the signal is going to look something like this when you add the signals together. With the interference. So we put everything on they interfere with each other, so they're going to add to each other. What is going to happen, like I said, when I filter out certain frequencies, because this signal, the one in black, is at a certain frequency. So if I cut out that frequency, I cut out the high frequency and cut out, just keep the one that I want, then it alone will come through. All right.
Okay, sir.
So that is why we do we take the signal and we break it up. If it was continuous now, then we would have a problem. Because a continuous signal is made up of several different frequencies mixed together to form the continuous signal. But when it's a digital signal, it's ones and zeros. But like I say, it's ones and zeros at the frequency at which they occur is constant. All right. So we're saying so we are saying that when we take a signal and break it up into parts. So we have to sample it and then we digitize it. We're not dealing with the digital, we are going to be dealing with the mathematics of a discrete signal, not a digital signal, not a digital system, not dealing with digital. We have another class for that. So when you take the 4 volts and turn it into 110, and then the 5 volts and turn it into 101 and 7 along, that's a digital system. So a digital system, we have mathematics to deal with that, but we're not dealing with that right now. So so let us talk about, first of all, not differential equations. I'm going to talk about when we have a difference equation. Yeah, FFE, RENCE Did you talk about difference equation in maths class?
Differential, sir.
Not difference?
Sir, go for a second, sir. Just for a second, please. Yes, sir, I can deal with it now.
All right. So I'm going to just start with a simple equation. Um, so and so if I have a filter, so what is the differential equation?
Sir, is it when we find a transfer function?
All right. So this here is 1 over, so let's use the transfer function approach. So this is 1 over 5s, and this is 10. And so this is going to be 1 over 5s over 1 over 5s plus 10 is V out over V in. So this is going to be 1 over 5s over 1 plus 50s over 5s. These two cancel. So we have that V out over V in is equal to 1 over 1 plus 50s. So that implies now if I cross multiply, then it's going to be 1 plus 50s V out is equal to V in. So S represents the first derivative, so let me rewrite it go the other way. So V out, I'm going to put that over here, plus, so that's 50 dV out dt plus V out is equal to V in. So this is the differential equation. So that's the differential equation. Now, when instead of looking at the system every on a continuous basis, suppose I look at it every t equals 0.1 second. All right. Suppose I look at it like that. So I'm looking at my V out every t equal 0.1 second. Then I just need to make a point here. All right. So in our system now, we are going to replace all of these things. We're not going to be looking. So let me put in the time just to. So this is the voltage. With the differential equation, we're looking at the voltage at any time t. But now, in the case of the discrete system, we are only looking at the voltages. So we blink, oh, answer what's the voltage. I'll blink again as the next voltage. I'll blink again as the next voltage. So every time we blink, we're looking at our voltage. So we're looking at the voltages, not as a continuous time, or I not open all the time, we're looking at it as discrete times. Right? So the thing is sampled and taken at discrete times. Now, you will agree with me that so the voltages that we are going to be seeing are going to be V. The voltages that we see is V at t, V at 2t, and V at 3t, and V at kt, and V at k plus 1t. So we are going to see the voltages at those times. So what we're going to do is in our differential equation, we are going to replace these voltages here by, we are going to see that V out at some time, which we're calling kt. Right, so k is 0, 1, 2, 3, 4, 5. And similarly, we're going to be saying that the voltage that input at kt. All right, but what do we do now for the gradient? So if because dV by dt represents the gradient. Now, how do we find the gradient between V1 and V2? That is a question. What do we gradient be? Is that a trick question?
So to find the gradient between V out and V in?
No, between V1 and V2.
V1.
Straight line equation that I use, sir.
Huh?
A straight line equation that I use.
Yep. You can't use anything else. You have to use a straight line. So what would the gradient between V1 and V2?
I have V2
2T, man. Minus T. And then you'll go V2 minus
V2.
Yes, sir.
All right, so what about the gradient now for k and k plus 1? How do we find that? So k represents any time, any voltage at any time, k equals 0, 1, 2, 3, 4, 5. So this voltage, how do we find this gradient here?
It would be the same way, sir.
Vk plus 1 minus Vk over K plus 1t minus kt.
All right. So what we are saying is that the gradient at any time t, that is what we're going to replace this. So we're going to write 50. And instead of dv out vt, we are going to use the discrete system, we have to use discrete gradient. So we're going to say v k plus 1 minus vk all over t is the gradient. All right, so that is what is going to replace my dv by dt. So now, so if I write this out and multiply by t, it's going to be 50 vk plus 1 minus 50 vk plus t, and this is, I'm sorry, this is v out. Plus t, and then this kt is the same thing as k plus 1 t and all those things. So we're going to put 50. What would normally be the out the t because it is understood. So this is v out for v in k. And we had said our t is, sorry, one second. T, we said t equal 0.1 second. So therefore, we're filling the value for t that is multiplied here. So that's 50 v out k plus 1. So this is 0.1. So 50 minus 0.1 is 49.9 v out of k is equal to v in of k. Now, this equation is called a difference equation. This equation that we have here is called a difference equation. So when we sample a system,
Sir, the 0.1 is
the sampling time,
okay.
we're looking at it every 0.1 second.
Okay, sir.
Sir,
Mm.
what happened to the t on the right hand side of the equation, sir?
You mean this t here? That
Yes, sir.
I'm saying that when we're looking at, we usually just assume that it is known that it's going to be k times t. All of these t's, we just assume that it is known that all of these k and k plus 1 have a t with them.
So, sir, in that
Oh,
case,
so it's
sir,
common
even
to
if,
both sides, sir.
Yeah.
so, sir, In that case, even the difference equation has the k's, the t's.
Yeah, all of them. So T, T, T. But we just leave it out because it is assumed known. So all of that shenanigan there was just to say that when we take a system and we sample it and we chop it up and we look at it in pieces, then we're going to see an equation looking like this that we have here. And that this kind of equation is a difference equation. So we want to look at, so whenever we take a system, sample it and look at it this at discrete times, the equation is going to look like that. All right. So we want to look at two methods of solving a difference equation. So and they use DE for differential equation and difference equation. So we want to look at how we would solve for the output y for difference equation.
Sir, because in the before you got the difference equation, the denominator, and there was a t being multiplied. So how do you get rid of the
The denominator, or should I multiply this by t as well? So this is t and this should have been t. So this is t. You multiply everybody by t. So I multiplied everybody by t to get rid of the t that was on. All right. So like I was saying, all of that shenanigans that I was doing there is just to say that, all right, we have begun to sample systems. Well, long ago we selling data as samples. And when we sample the data, if we are to find a description for the system, a mathematical description for the system, then that mathematical description will end up as a difference equation. For continuous time system, is a differential equation, but for discrete system, it's going to be a difference equation. So we want to just turn our attention to how we solve difference equation, because we want to know what is y at the output at time t equal 1, 2, 3, 4, 5, 6, 7, 8, just like with a differential equation. So now, this equation says that I take a value, a y, take our k plus 1, put in k plus 1 in there, put in k plus 2 in there, and I end up with the same thing because I end up with 0 and I put them together, I end up with 0. So I'm going to try yk is equal to, let me write a constant, c a to the k. Now y of k plus 1 is going to be equal to c a to the k plus 1. And y of k plus 2 is going to be c a to the k plus 2. So you plug those into the equation.
So you're integrating.
Well, I'm not integrating it now, just say y is equal to a to the k, something raised to the power k. So I'm just going to take the k, I'm not integrating it. I just replace, so I'll say this is yk. So if I change it to yk plus 1, then I have to change the power to k plus 1 as well. So that's k plus 1, so I put k plus 1, okay, I'm not integrating.
Okay.
So I'm leaving out the c. The c not really help us. So I'll leave out the c. It would work out the same way, but I just want us to focus on what we're going to be doing here. So therefore we get a to the k plus 2 plus 3a to the k plus 1 plus 2a to the k equal 0. So this is a to the k. If you use the rule of indices, a to the k plus 2 is a to the k times a squared plus 3a to the k times a plus 2a to the k equals 0. If we factorize all the a to the k, we're going to get a squared plus 3a plus 2 is equal to 0. Now, a to the k is never 0. So, therefore, a squared plus 3a plus 2 must be the culprit that causes the thing to become 0. And guess what this thing is called? This equation is called
Quadratic.
it's a quadratic equation, but when you're solving a differential equation, they have a name for when you end up with an equation like this.
The auxiliary equation.
Right. So this same thing in a difference equation is called auxiliary equation. And in engineering, so the auxiliary are characteristic equation. So to factorize it, the a equal -1 or -2, and then so therefore y is going to be equal to a to the minus minus a is minus 1, so sorry, minus 1 to the k plus minus 2 to the k. And what we do is we put an arbitrary constant in front because that does not change our solution.
Yeah, can I go for a second, please?
So, sir,
Mhm.
the C don't have no value.
Not now.
Oh, all right.
And sir,
Mhm.
for the C1 raised to the minus 1k, it's based because of the results you get for the roots, right?
Yeah.
Okay.
All right. So we want to turn our attention to this next difference equation. So the auxiliary equation will be what? A squared plus what?
That's 2A minus B.
2b, sir.
A minus 8.
So therefore, y would be equal to C1 4 to the k plus, sorry, minus 4 to the k plus C2 2 to the k. That's what my y k would be equal to. So now we're going to use y of 0 and y of 1 sort out. So we are told that y of 0 is equal to 0. So therefore, if we plug it in, you're going to get, we're going to plug in 0. Anything raised to the power 0. So if we plug in k is 0, anything raised to the power 0 is 1. So we're going to get C1 plus C2 is equal to 0. And then we have y of 1 is equal to 3. So we're going to put in 1 for k, and then y of k is 3. So therefore, we have minus 4. So C1 minus 4 to the 1 plus C2 2 to the 1 is equal to 3. So if we work out that, that's minus 4 to the 1 is minus 4. So that's minus 4 C1 plus 2 C2 equal 3. So establish simultaneous multiply by 2. So that's minus 2 C1. Sorry. Subtract.
Sir, C1 equal negative a half, C2 equal a half.
Alright, so we get C1 equal negative a half. Yeah. And C2 equal how much? Half?
Half, yes, sir.
Okay. So y of k is equal to negative a half minus 4 to the k plus a half um, 2 to the k. But those of us who more mathematically inclined, a half is 2 to the minus 1. So we can write this as yk equal negative a half, negative 4 to the k plus 2 to the k minus 1. All right.
Sir, question, sir. Sir, how you move from minus 4C1 plus 2 C2 equals 3 to 2C1 plus 2C2 equals 0?
Now, man, this equation up here, go to multiply by 2.
Okay, sir. To get it cancelled. Okay, sir. With two similar terms. Okay. Sir, could you scroll down a bit, sir?
So,
Or up, should say, sir. Up. Okay, sir. You could go down now, sir.
All right. So for this one, auxiliary equation is a squared plus 4a plus 3 equals 0. So a is equal to -1, -3. So therefore, you have that y k equals c1 minus 1 to the k plus c2 minus 3 to the k. So y of 0 is 1. So we have c1 plus c2 equal 1. Now we're plugging k equals 0. -1 to the 0 is 1, and -3 to the 0 is 1. Similarly, y of 1 equal 2. Plug in 1 for k. So we're going to get minus c1 minus 3 c2 is equal to 2. So we have c1 plus c2 equal 1, and minus c1 plus, minus 3c2 equal 2. We're going to get minus 2c2 equal 3. By that c2 is equal to -3 over 2, and c1 is going to be equal to 1 minus -3 over 2 is equal to 5 over 2.
Sir, when you find the roots, right, sir? Does it matter the order that you put it? So, for example, you put like -3 and -1.
No.
All right, sir.
So my yk will be equal to C1 is 5/2 -1 to the k plus C2 minus 3/2 -3 to the k. So that would be my sequence. Now, they want us to sketch the first 4 terms. So, I need to make up a little table. K, Y, K. So, K equals 0, K equals 1, K equals 2, K equals 3. So, those are my first 4 terms. Well, I expect y0 is supposed to be equal to 1, but let us try. Let us work it out. Y0 is equal to -5/2 minus 1 to the 0 minus, sorry, not -5/2, 5/2. Minus 3/2 minus 3 to the 0. So that is going to be 5/2 minus 3/2 equal 1. We also expect y1 to be equal to 2 because that's what we specified. That's 5/2 minus 1 to the 1 minus 3/2 minus 3 to the 1. So that is going to be minus 5/2. 3 to the 1 is 3. That's plus 9/2. So 9 minus 5 is 4/2 is 2. So as expected. So y of 2 is 5/2 -1 squared minus 3/2 -3 squared. So that's -1 squared is 1, so that's 5/2. Minus 3 squared is 9, 3 is 27. So 27 minus 5, that's 22, that's -11. By 3 is 5/2, -1 cubed minus 3/2, -3 cubed. So that's minus 5/2. 3 is 27. 27 is 81 plus 81 over 2. 81 minus 5. Eighty-one minus 5 is 76.
8.
Hmm?
38.
78 divided by 2, 39.
38, we get filled, sir.
How much?
38.
Oh, 38. All right. So if we are to make a sketch.
Sir,
Mhm.
question, sir. In the third line, you have 5 over 2 minus 27 over 2, sir.
Yeah.
And you have the answer is minus 11 over the side.
Mm-hmm.
No, sir.
Mm-hmm. Oh,
Oh, yes, sir. Never mind, sir.
all right. So now we have to make a sketch. Oh, I feel like cheating. So never cheat. I'm just going to plot it in Excel. Give me a second.
You go try use a different design to get the line.
Sir, it's a scattered chart type.
Yeah.
It's a scattered, we
Sorry, what do
say
you think you will drop out? Whenever I start again.
use a scattered for the chart type and we see the line drawing in there, sir.
Mm. Okay. Okay. So all right. So this would be our diagram. All right. So um so we're so what we have said is that when we digitize a signal, it becomes this when we discretize thing, we look at it at not over continuous time or at any time. We look at it at discrete time values. And when we look at it at discrete time values, then the equation that we use to represent the system is not a differential equation anymore, it's a difference equation. So the difference equation is represented and it can be solved in a similar way to a differential equation. Now, the thing about it is that as I have been solving the difference equation, yes, that's a legitimate method, but of course, we in engineering don't solve it that way. Just like how we use Laplace transforms, we use Z transform to solve differential equation, difference equation, and analyze difference equation. So we're going to talk about Z transform. All right, so we want to talk about the Z transform for functions. So we are going to start with the usual culprits. So the definition for the Z transform is summation from 0 to infinity of Z to the minus n multiplied by the function. So let's work on some Z transform. So let's work with the unit step. So the unit step function, as we have said before, is 1 for n greater than or equal to 0. And 0 elsewhere. So
Sir.
mhm.
Can you explain that the piecewise thing any further than how you have it here, or is it can just take it
This thing here, sir,
word for word or so?
what, which piecewise
Yes,
thing?
sir.
This that I have here? The
You
UN.
you of yes, sir.
No, so that is exactly what it said. It equal to 1 for n. So all of the values is only, remember now, when we talk about the step function continuous time, it just equal to 1. But if you sample it, there's still a unit step function. So that's what we're saying, that u of n are where we're just talking about it as a discrete system now instead of the continuous system. So we said this when it says UN of n equal 1 for all values 0 and over. So all of the values that we are going to put in for n. Sorry, this should be UNT.
Oh, like a binary system, sir.
Kinda, you can think of it in that way. So when we have that this function for all values of n, the value is 1. So if you find the Z transform of u of n, that's going to be equal to the sum from 0 to infinity of z to the minus n times 1. So that is going to be equal to z to the minus 0 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 plus going on. So if you write that down properly, that's 1 plus 1 over z plus 1 over z squared plus 1 over z cubed and so forth and so on. But I remind you of a geometric progression. Sum to infinity is a over 1 minus r. Hope you recall seeing that somewhere in your life at some point. And if you haven't seen it, the sum, infinite sum of a series, a is the first term and r is the common relation. Mean what you multiply the first term by to get the second term, what you multiply the second term by to get the third term, and so forth. So if we are adding this thing from 0 to infinity, so we're adding this 0, so the z transform of u of n is equal to a, which is 1, this is the first term is 1, over 1 minus r, and we want to multiply 1 by to get 1 over z is 1 over z. So that is equal to 1 over z, z minus 1. So z transform of un is equal to z over z minus 1. So the transform for the unit step function is that. All right. The next one we want to look at is the impulse function. And I'm basing the impulse function. We're saying that it occurs at a time A. So impulse function is equal to 1 when n equal A and 0 otherwise. So it's just a spike. So to aid our understanding, I'm going to find the impulse function, the Z transform of n minus 2. And so that is if A equal to, so it's equal to 1 at 2 and 0 otherwise. So we're going to take it's infinity. So we're going from 0 to infinity, Z to the minus n times minus 2. So when the only time that this function is going to be 1 is when n equals 2. So it's going to be 0 but when n equals 0, 0 when n equals 1, plus Z to the minus 2 times 1. This is when n equals 2. It's going to be 0 when n equals 3, and so forth. So you see where the Z transform for the impulse function at n minus 2 is equal to Z to the minus 2. And I want to write that in general, the Z transform of n minus A is equal to Z to the minus A.
Sir,
Mm-hmm.
you can explain where you have 0 plus 0 plus Z to the minus 1 times 1, right? That line.
All right. So remember now. All right. Let me put in another line. So I'm trying to get to that listing that is on the screen, but I'm not paying no mind. All right. So this is set to the minus 0, 1 minus 2, 0 minus 2, sorry, plus z to the minus 1, n minus 1, plus z to the minus 2, n minus 2, plus z to the minus 3, n minus 3, and so forth. Now, we said that the only time it sorry, we're putting the uh, so this is going to be 1 minus 2, this is going to be 2 minus 2, this is going to be 3 minus 2, etc. Now, the only time sorry, I'm going to have a little bit of problem with the technology. Okay. Whiteboard that. The marker. Thing graph. Something. No. Just not here. Whiteboard here. Yeah. So,
Okay, sir. So you're using the from the p-size function where it says n equal, where at 1 n is equal to a, and
yeah.
otherwise everything else is 0.
Yeah.
Okay, sir. 'Cause I was wondering how you get 3 minus 2 and still end up with a 0.
Sir.
Sir, can scroll up back a bit, please? All right, thank you, sir.
Sir, does this one have a name to it also?
So you have a plus 1 plus a plus 1 again, that mistake or it's supposed to be.
Sir. Sir.
Was I mute all this time?
Yes, sir. You're going to give us a sheet for this to like how they give us with the Laplace?
Yeah.
Alright, sir. So when would I expect that sheet, sir?
You know, typically later in the group.
Alright.
All right. So now, the fourth and fifth thing that I want to, because we're going to use them to solve our difference equation. All right. So I would like to the transform of Fn plus 1. So I'm going to say let the Z transform of F of n be equal to F Z. And let me just write that is equal to sum from n equals 0 to infinity of Z minus n Fn. And let me write out the first few terms. So this is Z to the minus 0 F of 0 plus Z to the minus 1 F of 1 plus Z to the minus 2 F of 2 plus Z to the minus 3 F of 3, yada 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 yada. So now Z of Fn plus 1 is infinity n equals 0. Z to the minus n of Fn plus 1. So if I plug in that, that's going to be Z to the minus 0. 0 plus 1 is 1 plus Z to the minus 1. 1 plus 1 is 2 plus Z to the minus 2 F of 3 plus Z to the minus 3 F of 4, etc. So now, if you look at these two functions, if I multiply this function if I multiply by Z, multiply this by Z. So I am going to say now, if I have Z, F of Z, this is going to give me Z, F of 0. I'm multiplying this by this function that I'm pointing to by Z. So I multiply Z times Z to the minus 1. It's going to give me F of 1 plus Z to the minus 2 times Z is going to give me z to the minus 1 f of 2 plus z to the minus 2 f of 3 and so forth and so on. So if you notice, the only difference between the terms up here and the terms down here is z f of 0. So therefore, I can write z of f n plus 1 is equal to, I'm going to carry, if I carry this function over on this side of the equation, then I end up with the z transform of f of n. So it's going to be equal to z f of z minus f of 0. And this f of 0 is called the initial condition.
Sir,
Mhm.
I was going to ask uh, what kind of system this would be applying to. I guess because there is no graph, so I don't really know how to apply it to.
Any kind of system, as long as you sample it, instead of looking at the thing continuously, whatever the system is, as long as you sample it, then you are going to end up with a difference equation. So we just want to write down the difference equation, but then just like how we use Laplace transform to solve the differential equation, then we use Z transform to solve the difference equation. All right, so we just establishing a few results, and then we give an example of a system that we apply. All right. The fifth one that we want to do is f of n plus 2. Want to find out the Z transform of f of n plus 2. So again, we note that that is going to be sum from 0 to infinity of z to the minus 2 f of n plus 2. And if we write out the first few terms in that, I write z to the minus n, sorry. So that's z to the minus 0, which is 1, f of n plus 2, which is also f of 2. When I put in n is 0, plus when I put in n equal minus 1, z to the minus 1, f of 3, plus z to the minus 2, f of 4, plus z to the minus 3, f of 5, and so forth. So compare this now. So now we have z to the minus f of 2, f of 3, and so forth and so on. So now, if we multiply everybody by z squared in the first equation, if we multiply everybody here in this equation, so z squared f of z is going to give me z squared f of 0 plus, when I multiply z to the minus 1 by z squared, I get z f of 1 plus, and this is now f of 2 plus z to the minus 1 f of 3 plus z to the minus 2 f of 4, etc. And once again, if we look at this up top, the corresponding values f of 2, f of 3, f of 4, and so forth. So what we can say is that if we take these values and carry them over to this side of the equation, these two values here, then we are going to end up with, we can say that the Z transform of Fn plus 2 is equal to Z squared f of z minus Z squared f of 0 minus Z f of 1. And these two quantities that are here are called the initial conditions. Oh, sorry, there's one more that I need.
Sir, was was wondering if instead of using numbers, could I just use n plus a and then increase it and reduce it. That's how you would do for the numbers.
All right,
You get a general
idea. Yeah, but basically we just going to be doing second order for the most part because we want to say now that if you take your electronic system and something, we want to work out a different equation, but then when we work out different equation, we want to work out what is the y value at each time interval that we get to look at it. But we're only going to be going up to second order. So that's why I want to work out the n plus 1 and n plus 2 case.
Sir, does the order matter with like the order of the circuit or that's a different?
No, the order circuit property. It does usually matter depending on what kind of circuit you are looking. Unless you are looking at a system like this. And then know on the other side. So we create a system in tree and the order does matter. which one comes first and which one comes second, because this is a filter. And this is over here is another filter. So let us say that this filter cut out all the 6 GHz signals, and this filter cut out all 80 GHz and below signal. And this amplifies, a certain, you want to amplify a certain thing. If the order is important in this particular case, so therefore the function, the Z transform, the discrete difference equation that you're going to get is going to be different if you reverse the order in which you put your G1, your G3, and your G4. So you're going to end up with a different equation each time. I don't know if that is answering the question.
Oh, all right.
All right. There's one that I forgot to do, so I'm going to just do it now and close so that next week, having laid this foundation, we can deal with the systems. Because I know that the question that you all asked, so all right, all of this math's very good for. So let me just deal with the 6 case. Should have done it earlier. Should have probably did it first. That's the most fundamental. So we want to find the Z transform of A to the N. So that's what we want to find. So we say that's the sum from 0 to infinity of Z to the minus N times A to the N. So we can write this as before we can fix this up as A over Z to the N. And it's going to be 1 plus A over Z plus A squared over Z squared plus A cubed over Z cubed, and so forth and so on. So if we use the sum of our GP, A over 1 minus R is going to be, so the Z transform of A to the N is going to be A, which is 1, over 1 minus R, which is A times Z, because multiply 1 by A to the Z, A over Z. So that is equal to 1 over, Z is the common denominator, Z minus A. So Z transform of A to the N is equal to Z over Z minus A. PowerPoint? Is that PowerPoint that? All right. Are you still hearing me?
Yeah, because if you have the thing there,